Okay, so hello everybody. I'm Tomoki Toda of the Nagoya University. And today I'd like to talk about the technology is called voice conversion. Okay, here I show the graph. So this is this graph comes from the Google Scholar. I have just counted the number of the citations of the typical three papers of the voice conversion. And in this class, let's quickly learn the voice conversion research history first. Okay, so that it starts around 1990, and then this technology has been gradually improved. And also, let's also look at the recent progress. Now we are in the deep learning period, so I will try to summarize the several important techniques. So first of all, let me introduce myself briefly. And I graduated from the Nagoya University in 1999. And then I joined the Nara Institute of Science and Technology, NICE for short. And my research topic was the voice conversion at that time. And I tried improving the performance of the basic technology of the voice conversion. After that, I was the postdoc at ATR, the CMU, and the Nagoya Institute of Technology. And at the time, I focused on the development of the applications using the voice conversion techniques. And then I came back to NICE as an assistant professor, and I started to improve the flexibility of the voice conversion system. And then I was the associate professor there, and my focus was one of the applications of the voice conversion, and that is called augmented speech production. And then I came back to Nagoya University as a professor, and recently we have just started the voice conversion challenge for evaluating the various voice conversion technologies using the common data set. Okay? So I think I must be a person who really enjoyed the BC research progress. And also, let me briefly introduce my lab of the Nagoya University. And this is a URL of my laboratory, but I'm sorry for only Japanese page. And this is a number of the lab members. I have just come back to the Nagoya University on September 2015. And then the number of the lab members have had gradually increased. So now we have around 20 members in my lab. So if you come to Japan, please feel free to visit our laboratory. And if you are interested in my laboratory as well, so please contact me. So we have several opportunities for the internship or a kind of the short visit. All right, so the self-introduction slide is this one. So we will hold the voice conversion tutorial at InterSpeech 2019. So the date and time is this tutorial will be held on September 15th, okay? And topics include an overview of the voice conversion techniques. But yeah, this one actually has the overlap with this class. But in this tutorial, we will focus on more this one, the direct waveform modification techniques. Okay, and then we also have the kind of the introduction of the freely available software. The first one is a Sprocket, and this is a BC toolkit. And in this hands-on session, you will learn how to use this one actually. But for this tutorial, we plan to implement the direct waveform modification techniques. Okay. But today, please use the current version using the old direct waveform modification. And then we also plan to introduce our developed WaveNet vocoder in order to make it possible to develop the VC system using the WaveNet vocoder. Okay. So if you are interested in this tutorial, please register from the InterSpeech website. All right, so here we go. So this is the outline of this class. I will explain the part is a voice conversion, VC for short, okay? And why is the VC technique needed, and how to do the VC, okay? And then I will introduce the VC research history and the recent progress, okay? So how to improve the conversion model, how to improve something, and so on, okay? And then I will summarize this class. Well, first, let's look at the VC technique, okay? So the VC is a technique to generate the speech sounds conveying the desired paralinguistic information or non-linguistic information. So this is a kind of my definition of the VC technique. VC is a technique to modify the speech waveform to convert the non or paralinguistic information while preserving the linguistic information, okay? So the input is the speech signal, and output is also the speech signal, okay? And by using this VC, we can convert this input speech signal as if it is uttered by a specific target speaker, the specific target speaker, or uttered by a specific target speaking star, and so on, while keeping the linguistic contents unchanged. All right, so there would be the two questions. The first one would be why such a technique is needed, because this looks very dangerous, right? So I can speak, for example, using Yanis's voice, very dangerous. But why such a technique is needed? So this is the first question. The second one is how can we do this voice conversion, okay? All right, so let's answer to the first question, why VC is needed. And VC has the potential to break down the barriers existing in our speech communication, okay? So in the speech production mechanism, we need to use our body, the speech organs. First, we need to generate the excitation signal using our vocal folds vibration, and then we articulate the generated excitation sounds using our speech organs, okay? Finally, we can produce the speech sounds. And now let's think about using the VC for converting this produced speech sounds, okay? What can we do? So we could augment our speech production by using the VC, okay? So now we may intentionally control non-linguistic information or paralinguistic information beyond our physical constraints. We may be able to generate excitation signal beyond the physical constraints, and we may be able to articulate the excitation signals beyond our physical constraints, okay? So that we can produce more varieties of the speech signal. So probably we could develop this kind of technique. So even if some speech organs were lost, probably he or she would lost their speech, the production function. So this is a problematic situation. But by using this VC techniques, so we could recover the normal speech organs, okay, by virtually implemented the normal one into her body or his body, okay. So this is one of the applications of the voice conversion. And let's listen to the samples of the vocally handicapped people. That's already in Japanese sample, but let's listen to this one. So this speech is called the esophageal speech, okay? And by using the voice conversion, this speech can be converted to like this. So can you listen to this audio? Okay. And this is another type of the vocally handicapped people's voice. So the very mechanical sounds, but it can be converted into this sound. I don't have the volume.
The sound comes from?
This one. No.
So then is it
So,
increased?
yeah, this is a max. Almost. I can do it.
Yeah, it's better.
Better. Okay. Now again, sorry for Japanese sample, but this is one of the applications of the voice conversion. So that this is a very useful technique for helping the people. Okay, so the next question was how to convert speech, how to do the voice conversion. Okay, so in the voice conversion, we modify the speech parameters. For example, using the source filter model, okay, which is called vocoder. So first, we have the input speech. This is analyzed to extract the speech parameters. And then these speech parameters are converted to the desired one. And then finally, we generate the converted waveforms from the converted speech parameters. Okay. So this is the typical process of the voice conversion. And by converting the speech parameters into the speech waveform, we usually use the vocoder, okay? So which is called source filter model. And now we have the speech signal. This one is modeled using this kind of the structure. This is the excitation generation part, and this is the resonance filter. So this structure is based on our speech production mechanism, okay? And the excitation signal is simply modeled by using the pulse train and the Gaussian noise. Okay, so first let's listen to the speech signal sound.
Author of The Danger Trail, Philip Steele's, etc.
And this is a pulse train, probably too loud. Here we go. Oh, this is a pulse train, okay, and this is a Gaussian noise. So we extract the fundamental frequency, I mean the F0, the frame by frame, and we control the period of this pulse train and switching timing between the pulse train and the Gaussian noise to generate this excitation signal. Okay, so these parameters are extracted from this speech signal.
Author of The Danger Trail, Philip Steele's, etc.
And extracted F0 values and unvoiced voice decisions, and we can generate this excitation signal. Okay, and then by using the extracted spectral parameter, I mean the spectral envelope parameter, we perform the filtering for adding the frequency characteristics represented by this spectral parameter. And this is the result.
Author of The Danger Trail, Philip Steele's, etc.
Okay, this is the excitation signal. And this is a vocoded voice.
Author of The Danger Trail, Philip Steele's, etc.
Okay, so this is a vocoder, okay? And now by manipulating the extracted speech parameters, we can convert the vocoded voice, okay? So here I will introduce a rule-based conversion based on the time invariant function. For example, for excitation parameters, such as the fundamental frequency, I mean the F0, we could convert its values higher or lower, okay? And for the spectral parameters, I mean the resonance parameters, we may manipulate the frequency axis. For example, we may extend this frequency axis like this. Physically, this one corresponds to make our vocal tract shorter, okay? Or we may shrink this frequency axis like this. And physically, this process corresponds to making our vocal tract longer, okay? So let me show you one demonstration. This is a real-time speech modification software developed by one of my colleagues. So this is a recorded voice. And now, if I click this button, the analysis synthesis processes is running. Here we go. So now sorry. Difficult. Anyway, so now the vocoded voice is played. And now because of the vocoder, we can control, for example, the F0 like this. Okay, so now my voice has a higher pitch. Actually, I speak usually, but you can listen to my higher pitch, very, very strange voice, or the lower pitch like this. Hello, can you hear me? Okay, so this is the Crete. Anyway, so this is the converted voice. So next, let's make the frequency axis expanded or shrinked. Okay. Now my vocal tract, my vocal tract becomes shorter, the version. Okay. So my voice quality sounds like this if my body is much smaller. Okay. And let's make my body bigger. Can you hear me? Actually, for Japanese, this kind of the voice quality is very familiar. We have the small extra. They are very big. They have this kind of the voice quality usually. And now let's make the control both of them. I mean the fundamental frequency and the vocal tract response. And I mean the resonance filter. So my voice becomes like this. Hello, can you hear me? So it sounds like the female's voice. Okay. So this is one of the example of the voice conversion using the rule-based conversion. Just by using the vocoder, we can do this kind of the conversion. All right. So by using the vocoder, we can convert our producer speech like this. But it is still very difficult to convert, for example, my voice into the specific target speaker. So how to do it? So by using the machine learning, we can do it. Okay. So the point is here, how to convert the extracted speech parameters. So by using the training data and machine learning technique, we can develop the more complicated conversion function to convert my speech parameters into the different speakers. I mean the specific target speakers, the speech parameters. Okay. So the statistical voice conversion can be achieved by using both the signal processing and machine learning. Okay. And this is a basic framework of the statistical VC. Basically, this process can be described as a regression. Okay, so in the traditional framework, we use a supervised training, using the utterance pairs of the source speakers and the target speakers. So here, I show the example of the speaker conversion. I want to convert this speaker's voice into that speaker's voice. First, we prepare the training data consisting of the same utterance pairs of the source and the target speakers. Okay, and this is an example of the source speaker's voice.
Author of the Danger Trail, Philip Steele's, etc. Not at this particular case, Tom. Apologized Whitmore.
And this is a target.
Author of the Danger Trail, Philip Steele's, etc. Not at this particular case, Tom. Apologized Whitmore.
So as Yanis explained, actually we use a very limited amount of the data. Here I just used only the 50 utterance pairs. Okay, so in the total duration would be around 3 or 5 minutes only. And then we train the conversion model using these utterance pairs. Once we train this one, we can convert the arbitrary utterance of the source speaker as if it is uttered by the target speaker. And this is an example of the source speaker's voice, not included in the training data.
It fairly clubbed me into recognizing it.
And this is an example of the converted voice.
It fairly clubbed me into recognizing it.
Okay, so while keeping the linguistic contents unchanged, we can convert only the voice quality like this. So let's look at the more details. So this slide shows the standard training process using the utterance pairs. So we want to model the correspondence of the source feature into the target feature. First, we extract the source features, the speech parameters from the source speech voices. And we also extract the target speech parameters. And then, of course, durations are completely different from each other. So we need to perform the time alignment between the source and target, the feature sequence. After this time alignment, we can develop this kind of the joint features consisting of the source features and the target features. Okay? And then now we can use this one as a supervised training data so that we develop the conversion model for converting the source features into the target, the corresponding target features. And once we train this conversion model, the conversion function, so that we can convert the arbitrary utterances of the source speakers like this. First, we extract the source feature sequence, and then we just apply this pre-trained conversion model to this sequence. Consequently, we can get this converted feature sequence. Finally, as I explained before, by using the vocoder, we can generate this converted speech waveform. Okay? All right, so I will show you one demonstration of the statistical voice conversion. And now I have developed the software to convert my voice into the famous virtual singer in Japan. So let's listen to her voice. I'm sorry, again, this is a Japanese song. And I will show you the very, very strange movie. Here we go. So this is an example of the real-time, the statistical voice conversion. Actually, for this class, I bring my laptop PC here, so that I will try to convert my voice now. Okay. Can you hear me? Let me speak in Japanese. So I can sing or I can talk using the very famous singer's voice. Like this. Actually, I developed this conversion model using my Japanese song, my Japanese singing voice. But this conversion model is a kind of the language independent, so that it may convert my English as well. Like this. Okay. So, yep. Can you sing?
Can you sing with your natural voice like that?
I see. If I implement the F0 conversion as well, we can do it. But here I didn't do it. So that's why I use my falsetto. So, something like this. I have never do the F0 conversion. Probably doesn't work. Sorry, I didn't implement. So anyway, in this case, I trained the conversion model using my falsetto and the famous virtual singer's voice. So that's why when using this software, I need to sing using my falsetto. Okay. So this is a completely data-driven approach. So if we use the falsetto in the training, we need to use the falsetto in the conversion as well. Okay. All right. So this slide shows various BC frameworks. The typical BC framework is this one. As I explained, we use speech as an input, okay? And this framework is very effective for the real-time processing. So this is probably that we could develop the applications for the human-to-human communication because it works in real time, okay? So this is great. So the frameworks would be this one and this one. So that we could use the text as an input as well. So this is a TTS actually. So now we can control the output speech from the TTS by using the voice conversion as we want. The last one is the kind of the mixture. We may use not only speech but also the text as an input. Okay. So by using both of them, we can more carefully control the voice characteristics of the converted speech. Okay. So there are the three main frameworks, but in this class, we focus on this one, the first one. The speech is used as an input. Okay. And finally, let me explain the difficulties in handling the speech waveform. So we need to properly model the acoustic characteristics of the speech waveform. But as you know, the speech signal has underlying this kind of the hierarchical structure. So we have the sentence. The sentence consists of the multiple words. And each word consists of the multiple phones. And each phone corresponding to the waveform segment, okay? So basically there is the long-term dependency over this speech waveform. So we need to model such a long-term dependency. We need to model the dynamics of the speech waveforms. The other is the fluctuation component, I mean the stochastic component. Because we use our speech organs to produce speech sounds, even if we say the same things twice or three times, actually we can observe the completely different speech waveform amplitude, okay? So this is a highly stochastic signal, and we need to carefully model such a stochastic components. Otherwise, the synthetic voice sounds very muffled or very noisy and so on. So it is very important to accurately generate these fluctuations. All right, so this is a kind of the brief introduction of the voice conversion. From now, I will look at the VC research histories. So this slide shows the process of the statistical VC. As I explained before, so we have these components, these procedures for the voice conversion. So in order to improve the statistical VC, so there are several research topics. The first one is the improvement of this one, the conversion model. Okay? This is a very popular research topic in this voice conversion area. The other would be the improvement of an objective function, because this is the regression problem. So it is very important to use the appropriate objective function for generating the naturally sounding converted voice. The third one is the improvement of the waveform generation. Recently we have the big progress of the deep learning for generating the speech waveforms. So now we can change the vocoding technique. The next one is the flexibility. In the previous slides, I explained kind of the supervised training framework. In such a framework, we need to use utterance pairs of the source and the target voices, but it is not so flexible. So there are lots of the research topics for improving the flexibility of the training. The next one is how to compare the various types of the techniques. Okay, this is a data-driven approach. So in order to carefully compare the different techniques, actually we need to use a common data set. Okay, so I will introduce our activity to do it. So last one is applications. So this is a very basic techniques. So we could develop the various types of the applications using the statistical VC. All right, so I will explain the research topics one by one. The first one is the improvement of the conversion model. All right, so the key ideas are how to accurately model the nonlinear regression and how to model the speech dynamics, okay? And the pioneer work of the statistical VC is this one. The first, the vector quantization is used to develop the voice conversion. This is a frame-based discrete mapping. And this one was extended to the GMM, so by the Yanis. And soft clustering and linear regression have been successfully implemented for the statistical VC. Furthermore, in order to model the dynamics of the speech features, we propose the trajectory conversion. And of course, some researchers proposed the use of the neural network for modeling this nonlinear mapping. And thanks to the progress of the deep learning, now lots of the researchers focus on developing the deep learning technique for the statistical VC. So first, by using the distributed representation, the RBM has been successfully implemented for the statistical VC. And then this one becomes a deep learning, deep network, okay? And recently, to model the dynamics of the speech sounds, the speech features, the various types of the networks have been proposed, such as convolutional layers, the recurrent layers, and encoder-decoder, as the previous lecturers explained. And we also have another approach based on the exemplar or the sparsity constraint. The typical one would be the unit selection or non-negative matrix factorization and the Gaussian process regression and so on. So this is a non-parametric model. But in this class, I will briefly explain these techniques from the parametric model approach, okay? And this one is a traditional one. First, I will explain these traditional techniques. This is the mixture model-based approach. And then I will briefly summarize the recent progress by using the deep learning techniques. So this is a product model approach, okay? So the frame-based conversion is a the most simple approach for the statistical VC. So that we convert the speech features frame by frame independently, okay? We extract these speech source feature vectors from the source speech signal, and then we convert these features frame by frame, okay? So here the X sub t shows a source feature vector, and the Y sub t shows a target feature vector, and the statistical model parameter set is given by lambda, and the Y sub t hat represents the converted feature vector, okay? So the frame-based conversion function can be described like this, okay? So in order to determine the converted feature vector at frame t, we need to use only the source feature vector at the same frame. Okay? This is a frame-based conversion. And the pioneer work was the VT-based, the vector quantization-based conversion, as I explained. And in this framework, first we extract the source feature sequence, and then by using the training data, this source codebook and the corresponding mapping codebook have been developed. Okay, and by using this source codebook, these extracted source feature vectors are encoded into the index of the centroids of this source codebook. Okay, So now this source feature vector sequence is represented by the sequence of the VQ, I mean the vector quantization index, okay? And then by using this mapping codebook, this VQ index is is replaced with the corresponding centroid of this mapping codebook. This is the VQ-based conversion, very simple. And usually we convert only the spectral parameters by using this one. And the other parameters, such as F0, and is converted using the very simple function, such as a time invariant linear transform. So this is the discrete mapping. Here, this figure shows the data distribution. The horizontal axis shows the input, the source feature, and the vertical axis shows the targets, the source feature. This contour line shows the kind of the histogram of the data distributions counted using the training data. And by using the VQ, we just quantize these input features into the first index and these parts into the second index. And then this first index, the values are converted into the first centroid, this value, and this one is converted to this one. So by using the VQ-based conversion, we can use this kind of the mapping function. Okay. Yes.
Can you use the microphone?
How do you determine the amount of quantization, like the granularity of that for the codebook?
All right, so we need to carefully determine the proper number of the centroids, basically. It depends on the amount of the training data. And there is a trade-off between the kind of the accuracy of the modeling and overfitting. Yeah. So that we empirically determine the appropriate number. So that is a pioneer work. The next one is the progress done by Yanis. So now our society changed the discontinuous conversion mapping function into the continuous mapping function. So we want to model the feature correlation more accurately. So here I will show you again the VQ-based conversion case. But by using this continuous conversion, we can extract this kind of the continuous mapping function. And we can well model the correlation between the input features and the target features. So this is called the GMM-based conversion. So I will briefly explain this one. So in this conversion, we model the joint PDF probability density function using the supervised training data. So the X sub t is the input feature, Y sub t is the output feature. We train the GMM. Okay. So by using this one, we model this joint PDF. Okay. So the observation vector is given by this joint feature vector consisting of the source features and the corresponding target feature. And the GMM parameter set consists of the mixture component weights, mean vectors, and covariance matrix. Okay? The feature correlation between the source and target is well modeled by using this covariance matrix and the mixture of the Gaussians. Okay? And this is the training process. In the conversion, we can analytically derive this conditional PDF from this joint PDF by using this equation. Okay. So this one is also modeled by a GMM. Okay. So we can easily calculate, for example, the MMSE estimate using this equation. So this is the GMM-based conversion. And finally, we can get this kind of the continuous mapping function. Okay. So the next progress is the from frame-based conversion into the sequence-based conversion to model the inter-frame correlation over nanotrans. Okay. So we want to model the speech dynamics more carefully. So previously we used the frame-based conversion. And now, in order to consider the interframe correlation, the sequence-based conversion was proposed. Okay? In this conversion framework, we convert all of the source feature sequence simultaneously. Okay? In other words, in order to determine the result of the last frame, we need to use all of them. Okay? So this is the sequence-based conversion. So in this framework, so first we train the conversion model using not only the static features, but also the dynamic features. So first we calculate the dynamic features, I mean the delta feature, the frame by frame, and we extract the joint feature vector for the source, the voices. And we also develop this kind of the joint target features consisting of not only static, but also the dynamic features. And then we train the GMM, okay? So now the observation vector consists of not only the static source and target, but also the dynamic source and target, the feature vectors. And then we get the joint PDF, okay? So the difference is only the definition of the observation vector. But in the conversion, we have the big difference. So now, again, we extract the source feature sequence, consisting of not only static, but also the dynamic features. And then we use this objective function. So now we also have the conditional PDF, but it consists of the two parts. The first one is a conditional PDF for the static features of the target. Okay. The other one is the conditional PDF for the dynamic features. And these dynamic features can be calculated from the static feature sequence. So we can look at this objective function as the function of the only static features. Okay. So again, the dynamic features can be calculated from the static feature sequence. So that's why this one can be regarded as a function of the static feature sequence. That's why we can analytically determine the converted static feature sequence by maximizing this objective function. Okay, so all of these converted static feature vectors over Natrans are simultaneously determined using all of the source feature vectors over Natrans. And this is the sequence-based conversion. All right, from now I will explain, I will introduce the progress of the voice conversion, the mapping function, based on the deep learning, okay? So in the GMM-based conversion, we use the mixture model, okay? So this is the relationship between the variables. X is a source feature vector, Y is a target feature vector. And we have the hidden variable, Z, okay? So in the mixture model, this latent variable is given by the one-hot representation. Okay? So if we use the M mixture component, this one has the M-dimensional vector, okay, one-hot M-dimensional vector. This is the joint PDF modeling based on the GMM. But in the product model, like the deep learning, I mean the neural network, so we use the distributed representation, okay? We don't use the one-hot vector. We use the combinations of the 1 or 0 at each dimension. Okay. So let's think about the number of mixture components. Here we have only M Gaussians by using the M-dimensional latent vector. But by using the distributed representation, we can generate the 2 to the power M Gaussians. So the product model has a much higher representation power, okay, compared to the mixture model. So some researchers implemented this product model to the voice conversion. Okay. And in order to robustly train the deep generative model, I mean the deep network, they developed this kind of the training procedure. First, we separately train the restricted Boltzmann machines for the source features and for the target features. The RBM is a generative model, so we just train this kind of the RBM separately using only the source voices or only for the target voices. And then after training these RBMs, we infer these latent vectors, right? And then we train the network for modeling the joint PDF, the probability mass function between this latent vectors and this latent vectors, okay? And actually, this is called the bidirectional associative memory, the BAM, okay? And then by combining these networks, we developed this deep network, okay? So the source feature vector is encoded into the distributed representation. And then this distributed representation is converted into the target ones. Finally, based on these distributed representations, we can infer the target feature vector. And then, there are lots of the methods for implementing the more sophisticated network, such as the CNN, convolutional neural network. So one of the previous work is to use the gated CNN. Okay, so this is now very familiar. This is very effectively model the long-term dependency. So the source feature sequence is converted using the CNN here. Okay. So the gated CNN, the operation is given by this one. So we have the linear convolution here, and we have another convolution here. So by using the sigmoid function and the element-wise product, we develop the nonlinear mapping. Okay. So this is a schematic image. So this axis shows the time, and this axis shows the feature dimension, and this shows the channel of the convolution. Okay. So this one is filtered using this one. Okay. And we also have the different linear filter, and by using this sigmoid function, we develop the gated structure. Okay. This is the output, and then this one is propagate to the next layer. So this is a gated CNN. And in order to train this network, we usually use the fixed length of the sequence for training the gated CNN. So this is the training process. But in the conversion, because of the CNN, we can handle the arbitrary length of the sequence. Okay. So this is one example for extending the deep network into the sequence-based network. Another example is, of course, the recurrent neural network. Okay. So as you know, the bidirectional LSTM is very effective for modeling the interframe correlation over nanotrons. So some researchers have successfully applied the bidirectional recurrent network to the voice conversion task. Okay. So now because of the bidirectional structure, we have the forward propagation and backward propagation. Okay. And then these latent features are propagated into the next layer. And these forward and backward LSTMs are stacked to develop the deep structure. Okay. So by using this network, we can handle the interframe correlation over nanotrons. Okay. So this is the second example of the sequential model based on the deep learning. And recently, some research groups that have successfully implemented the encoder-decoder to the voice conversion. Okay. So they implemented the encoder-decoder based on the attention mechanism for converting the source feature sequence into the target, the MER spectrogram, actually. So in this framework, the conditional model of the target sequence given the source sequence is directly trained using the encoder-decoder network. Okay. So now we can handle the different lengths of the feature sequence. Okay. And because of the encoder-decoder, we can convert not only the short-term features such as the spectral parameters, but also the long-term features such as the prosodic features. For example, the F0 patterns, duration, and so on. Those prosodic parameters are also converted by using this encoder-decoder framework. Okay? So the source feature sequence is converted into the latent feature sequence using the encoder. Okay? We usually use the recurrent network or convolution network, or the combination of both of them. And then by using the autoregressive decoder, based on the RNN with the attention, actually they use the location-sensitive attention here, we can generate the target feature sequence one by one. Okay? So this is the autoregressive structure. And because of the neural network, we can handle the high-dimensional feature sequence easily, so that they directly generate not the speech parameters, but just the mere spectrograms, including the harmonic components. Okay? So this one includes the effect of the F0 as well. So the very complicated feature sequence can be well modeled using this structure. So let's listen to audio samples. Oops. Oh, sorry. Oh. Yes. So this is a male voice.
而我竟感觉有一种难以言说的忧伤涌上心头。
And this is a female voice.
前方桥下测丁字路口，准备进主路。
This is an example of the converted voice from female to male.
而我竟感觉有一种难以言说的忧伤涌上心头。
And male to female.
前方桥下侧丁字路口，准备进主路。
Again, listen to the male voice.
而我竟感觉有一种难以言说的忧伤涌上心头。
And female voice.
前方桥下测丁字路口，准备进主路。
Of course, voice qualities are completely different, but the prosody is also different from each other. But such a prosodic difference can be well converted by using the encoder-decoder. Okay. Again, let's listen to this is a female.
前方桥下测丁字路口，准备进主路。
And this is a converted voice.
而我竟感觉有一种难以言说的忧伤涌上心头。
And this is the target.
而我竟感觉有一种难以言说的忧伤涌上心头。
Okay. And this is a male voice.
而我竟感觉有一种难以言说的忧伤涌上心头。
This is a converted voice.
前方桥下侧丁字路口，准备进主路。
And this is a target female.
前方桥下侧丁字路口，准备进。
Okay, so the kind of the speaking style is also well converted by using this encoder-decoder framework. Yes.
I hear some clicks in the converted signals. Why?
Well, actually this one was developed by not me, but the different researcher. But I guess they use a WaveNet, and the WaveNet generates such a pulsive noise.
Thanks.
Okay.
So I had a question. For this one, I understand what the loss function would be. It would be just the log probability of the target given the source. For the previous two slides, is it the same? And kind of what's the loss function and what's the is it? Yeah.
Right. So actually there are the several variants of the loss function, but here they use not only for example, the distance-based loss function here, and they also use a kind of the classification error of the ASR. So that they implement the various criterion for optimizing them.
And the CNN one that was two slides before?
here they just use a very simple loss function, but the L1 loss, I guess.
Okay, so it's just deterministically outputting something at the sequence level, and then you're computing the L1 at the sequence level.
Yeah.
Thanks.
Yeah, when using the prior data, most of the researchers just use a very simple loss function. Okay, any other questions? Okay. All right, so this was the first part, how to improve the conversion model. The second part is the improvement of the objective function as the question, okay? So the key ideas are how to keep or how to reproduce the natural speech fluctuation. I mean the stochastic components. And how to handle the errors of the time alignment. This is also important. But as I explained in the previous slide, now that we have the encoder-decoder network, so this one can be addressed, okay? So traditionally, we use just the minimization of the regression error, okay? And by using the probabilistic model, we can formulate this process as a maximization of the likelihood function of the model. And now in the speech synthesis, actually minimizing the error is not so sufficient. I mean, sometimes it just generates very averaged result. I mean, the averaged spectral envelope, and it sounds very muffled. So we propose the regularization method capturing the stochastic components. I mean, the fluctuation over nanotolerance. Okay, that is called the global variance. And we also extended this one into the modulation spectrum over the spectral components. And recently, we have the GAN, okay, so the generative adversarial network. So now we can develop the data-driven regularization criteria, so that we can also train the metric for detecting the difference between the synthetic voice and natural voice, okay? And there are several methods for handling the misalignment problem, but now we have this encoder-decoder, so I will skip this one. So let me briefly introduce these techniques, okay? The first one is a global variance. So the global variance, or GB for short, is just calculated the standard deviation over nanotolerance, okay? So we have the feature vector sequence, and then we just calculate the variance of this one over nanotolerance. That is a GB, okay? So the idea is we want to keep the variance values so that it is very close to the natural one, okay? If we use only the minimization of the error, sometimes the variance becomes much small, okay? So that we want to avoid making the variance of the generated one too small, okay? So that's why we try to model this variance value directly. So the training process is very simple. So we have the feature vector sequence from the target, and then we calculate just the variance vectors in each utterance. So utterance by utterance, we extract the variance vectors. And then we model the PDF of the GV vectors. That's it. And then in the conversion, we add one more term here. So basically, as I explained before, we can use the multiple objective functions. The first one is a conditional PDF for the static features. The second one is a conditional PDF for the dynamic features for accurately modeling the speech dynamics. The last one is a new one, the PDF of the GB, okay? So now we have the 3 experts, okay? So that we calculate the product of these 3 experts, and we determine the ML estimate for maximizing this likelihood function, okay? So we can say that this is a kind of the regularization term, okay? So under this constraint, we try to maximize this previous likelihood function. And this is a conversion process, but we can implement the same, almost the same objective function in the training, okay? All right, so again, this is the function of the static features only, so that we can determine the static feature sequence that maximizes the likelihood function of the product of the experts, okay? And we can also implement much simpler approach. That is a post filter. So by using the training data, we can get the converted features without using the GV regularization term. And then we just design the post filter to enhance the GV values, okay? So this kind of the simple approach also works very well. And the GV idea can be extended into the more generic features. That is a modulation spectrum. So this is a feature trajectory that we can decompose the feature trajectory into the sinusoidal waveforms. Okay, so we just use a kind of the discrete Fourier transform. So we can decompose this trajectory into the individual sinusoidal waveform. Okay, and then we calculate GV of the individual sinusoidal waveforms. So this is called the modulation spectrum. Okay, so in the GV, we just calculate the variance of this original feature vector sequence. But in the modulation spectrum, we decompose it into the individual modulation components, and then we calculate the GV values. Okay, the idea is very simple, and then we model the modulation components as done in the GV modeling. Okay, so again these values are also calculated from only the static feature trajectory, so that we can determine the converted static feature sequence that maximizes the likelihood of the function consisting of the traditional GMM, the PDF, and also the PDF of these modulation components. Okay, and we can also incorporate this kind of idea into the training. Okay, so this is a work done in 2016, and now that we have the GAN, so by using the generative adversarial network, we can address this kind of the handcrafted features problem. Okay, now that we can develop the objective function based on the completely data-driven manner. So now we have those features here, and we want to convert this one using, for example, some networks. Okay, and this is a converted features. And traditionally, we just use a conversion error between the converted features and the target features. Okay, and now in the generative adversarial network, we use a discriminator here. Okay, and the discriminator tries to discriminate between this one and this one. Okay, if the converted features are used as an input, this one want to generate 0. Okay, if this natural one is input, this one want to generate 1. Okay, so this is just a discriminator for the handling for determining whether or not input is converted or natural. Okay. Yes.
Sorry, I had one question about this. People have found it hard often, I think, to have GANs which operate on very long sequences where the discriminator just has to make a decision between whether the entire sequence is real or fake. Is this addressed in some way? Do you use short snippets of sequence or?
I see. In this slide, we just show the frame-by-frame discriminator, but I had the next slide, but I cut it. But at that slide, we use a convolution network. So in the training, we extract the fixed length of the sequence, and then this one is passed into the CNN, and we also use this CNN as a discriminator. Yeah. So anyway, so by using this discriminator, we can calculate the adversarial loss. So we can optimize this conversion network using not only this conversion loss, but also the adversarial loss. So we want to fake the discriminator by optimizing this network, okay? So I think some previous lecturers have already explained the generative adversarial network, so I will skip this one. And as Matt have the question, if we want to handle the sequence of the features, we can use, for example, the CNN here or here, okay? So by using the gated CNN, we can use a sequence of the features as an input, okay? And this sequence is used as an input of this discriminator as well. So that we can perform the classification, the sequence by sequence, okay? Now that is a training. In the conversion, we need to use only this conversion network. And this is also CNN, so that we can handle arbitrary lengths of the sequence, okay? So let me explain the third one, and then let's have the break, okay? So let me explain this one, the improvement of the waveform generation. So in the third topics, the key ideas are how to leverage the source waveform, okay? The other is how to avoid assumptions in the source filter model. And as a typical approach to leverage the source waveform, we have the waveform modification based on the PSOLAR. But recently, we proposed the direct waveform filtering method. So in this framework, we directly estimate the time variant filter for modifying the input speech waveform. And recently, this one can be further extended into the more generalized implementation. And the other approach is directly improve the vocoder, okay? So traditionally, we have several very good high-quality vocoders, but there are limitations, okay? But recently, there are several improvements. The first, lots of the researchers tried improving the excitation part, okay? So they tried improving the excitation modeling in the vocoder. And some researchers have also applied the GAN to model the excitation signals. Recently, we have the neural vocoder. This is great, so that we can now generate the very naturally sounding the waveform. And some research group that has developed a kind of the CNN-based post-filtering. And this post-filter can be applied to the synthetic waveform for enhancing the synthetic waveform directory. So I will explain these methods one by one. The first one is a direct waveform modification. So in this framework, the input speech waveform is directly converted into the target one by using the time variant filter, okay? So we don't use the vocoder here. So we just use the time variant filtering here, okay? So in this framework, we need to estimate this one, the time variant filter. This one can be represented as like this. This is a frequency response of the source, and this is the frequency response of the target, okay? So we directly estimate this one, differential filter, okay? And if we use the GMM as a conversion model, we can directly analytically derive the differential GMM, okay? Originally, we modeled the joint PDF of the source and the target. But by applying this variable transformation, we can analytically derive the joint PDF of the source and differentials, okay? So by using this one, we can directly estimate the sequence of the log spectral differentials. For example, the sequence of the Merck epsilon, okay? So given the source features, we can directly estimate this one as a converted parameters. And by using the differential Merkel-Capsams, and we can design the time variant filter, and this designed filters can be applied to this input speech waveform directly. Okay. Actually, in the previous demonstration, we used this framework. So by using this framework, we can keep the phase components, so that it sounds very natural. And again, this one is very robust against the external noise, for example. And we can also alleviate the over-smoothing effects in this framework. But we have the problem, so it is still hard to convert the excitation parameters. So the many researchers have tried to improve the excitation modeling. Now this is a traditional vocoder framework. Here is the excitation part. Traditionally, we use the very simple excitation modeling, but lots of the researchers have improved this part. The first one is how to model the stochastic component. So we proposed the use of the parameterization of the frequency-dependent aperiodicity. Okay, and we can convert such stochastic components using the traditional stochastic probabilistic model. The other is phase component modeling. So there are lots of the research for the accurately model the phase. Okay, so some researchers tried using that template-based approach to model the one-pitch phase. Or some researchers have proposed the waveform, the reshaping filter. And some researchers developed the method for generating the one-pitch residual waveform data set and select the best one. So this is like the unit selection. So we develop the one-pitch residual waveform data set, and then we select the best one in the conversion. And recently, the GAN has been successfully applied to the excitation modeling. So by using the DNN, for example, we can generate the Grother pulse waveform very accurately. But this one doesn't include the stochastic component, because this is the kind of the deterministic mapping. Okay, but by using this one, we can generate the very good deterministic component of the Grother pulse. But now we want to generate the stochastic component as well. So we use the generator network for generating the stochastic component. And then the final one, final Grother pulse is generated by just adding the deterministic component and the stochastic component. And now the problem is how to train this network, okay? Because of the stochastic component, it is not so easy to directly train this one. So they use the GAN, okay? So again, they use the discriminator here. So they have the natural target Grother pulse waveform, and they have the generated Grother pulse waveform. So by using this discriminator, we can calculate the adversarial loss for optimizing this network, okay? We try to fake this discriminator by optimizing this network. And then finally, by using this trained network and this trained network, we can generate the Grother pulse waveform. And then we just perform the PSORA to generate the excitation signal. So the last one is a neural vocoder. So in 2016, the DeepMind has proposed a WebNet, okay? So it was good. And this is a great, it is also helpful for developing the vocoder. Originally, the WebNet was proposed as the TTS method. That was the mapping function from the linguistic features into the waveform. But this one is very generic, so that we can easily apply this one into the vocoder part only. Okay. So we have investigated the effectiveness of the target speaker-dependent WebNet vocoder, and we have found that it can generate speech waveform almost indistinguishable from the natural waveform. So this is great. And we can we can also use the wavenet vocoder as a kind of the post-processing for the voice conversion. So now that we have the traditional voice conversion framework, right? And then by using these converted speech parameters, that we want to generate the converted speech waveform finally. And in this part, that we can use the wavenet vocoder. Okay. Instead of using the traditional vocoder, that by using the wavenet vocoder, that we can significantly improve, for example, the conversion accuracy on the speaker individuality. And we can possibly also improve the converted speech quality. But in order to do it, we need to carefully train the wavenet vocoder in this framework, because this is a voice conversion. So here we would have the feature extraction error, and we also have the conversion error. So the input of the wavenet that suffers from the lots of the errors that we need to handle this kind of the feature sequence. So recently we proposed the fine-tuning method of the wavenet using the cyclic framework. So the main idea is to generate the training data for performing the fine-tuning of the wavenet vocoder. Okay. So this one is a converted features from the source, the voices. So now we want to convert the converted features into the target waveforms. Okay. The most simplest approach is to train the wavenet vocoder from these converted features into these target waveforms. But actually this kind of the framework doesn't work, okay? Because the temporal structure of this one is completely different that of this one, okay? So this one comes from the source features, and this one comes from the target speakers. So the temporal structures of this one is different from this one. So by using such features and such waveforms, actually the wavenet training doesn't work very well. Okay. So our idea is to use the one more network. So now we want to convert these converted features so that the wavenet can easily handle this one. Okay. But we need to reduce the acoustic mismatch between the training and the conversion. And we also need to handle the temporal structure mismatches between this one, okay? So we still have the temporal structure mismatch here. This one has different temporal structure of this one, okay? So we use the cyclic framework. So we extract the target features and we train another network from the natural target into the converted one, okay? So this is a kind of the network from the converted space into the natural space. And this one is a network for converting the natural space into the converted space, okay? And by using this one, these target features are converted to this one. And this should have the acoustic features similar to that one. And this one is further converted by using this one to this one, okay? So now the acoustic characteristics of this one should be similar to this one. And the temporal structure of this one is equivalent to this one, okay? So now by using this one, we can train the wavenet, okay? So in this framework, these two RNNs are jointly optimized using the two loss functions. The first one is a DTW loss here. So this one should be close to the target features. But we have the difference of the temporal structures, so we need to use a DTW here. The other loss is a cyclic loss. So we can also calculate the kind of the different distance between this one and this one. And the temporal structures of these two vector sequences are completely equivalent, so that we can directly calculate this cyclic loss. Okay? And by using both of them, we can jointly optimize these two networks. Okay? And after that, we can generate the cyclic converted features. And this one can be used as a pseudo training data for the WaveNet vocoder. Okay. So this framework works very well. So by using this one, we can significantly improve the performance of the WaveNet vocoder in the voice conversion framework. Okay. So the last one is a wave cycle GAN. Okay. So this is an approach for developing the convolutional network as a post filter of the synthetic waveform. So the purpose is to develop this gated CNN. This one converts the synthetic waveform into the natural one. Okay. So we want to make the output of this gated CNN similar to this natural waveform. Okay. But it is still very difficult to directly train this gated CNN because there are several differences between this natural waveform and this one. This is the time domain, the processing. So the phase differences are very, very important. So of course, this one has a different phase component of this one. So it is very difficult to directly calculate the distance between this one. Okay? So they use the GAN again. So they also have this gated CNN for converting the enhanced waveform into the synthetic waveform. Okay? So by using these two networks, so that we can calculate this cyclic loss. Okay? And we can also use this discriminator. Okay? So by using this discriminator, we can calculate the adversarial loss. And using both of them, we can optimize these two networks. And we also use one more loss, that is the identity mapping loss. So here, this CNN is basically convert this enhanced waveform into the synthetic waveform. But we just use this synthetic waveform as the input of this network. So this is a kind of the many-to-one mapping, okay? So the arbitrary input is converted into the synthetic voice. This is a kind of called the identity mapping loss. And this is also very helpful for training the network. And we also have the inverse direction. So now we have the natural waveform. By using this network, we can convert this natural waveform into the synthetic waveform. And then by using this network, we can further convert this one into this natural space. And we can calculate cyclic loss here. And by using the discriminator, we can calculate adversarial loss. And we also use the identity mapping loss here. So by using these 6, by using these 6 losses, we jointly optimize these two networks. Okay, so this is the wave cycle GAN, and by using the trained this network, we can enhance the synthetic waveform as if it is sound like the natural waveform. Okay, so this is a wave cycle GAN. This is a post-filter approach.
Sorry, I had one quick question on that. For the normal cycle GAN, it's often been observed that it kind of secretly encodes information in a way that's not immediately visually perceivable. But if you go from an image to a stylized map and then back to the image, you get something which is one of the things that cycle GAN's been used for, converting kind of maps into satellite. You get something which looks way more like the image than it should. Because it secretly encoded some information about the original image in the map representation. And this ultimately happens because cycle GAN is non-probabilistic, unlike the original GAN, which is probabilistic. And you can make cycle GAN probabilistic, but anyway, I just was wondering if you know if anyone's observed that. It's sometimes called stenography, like the secretly encoding information. If anyone's observed that here.
So I don't know that. Yeah, but as you know, that now that we have the lots of the archival papers, so somebody, I'm sure, I don't know it. Yeah. So anyway, so they just use these losses. All right, so this is a wave cycle GAN. Right, so the more details that will be presented in the VC tutorial. So we have the recent progress of the directed waveform modification, and we have successfully proposed more generic version of the direct waveform modification. By using this one, we can also convert F0, and we can use not only the differential model, but also the arbitrary conversion model, such as a BAE. And we also have the recent progress of the neural vocoder. Actually, now the neural vocoder is a very hot research topic in this society. But we also improved the wavenet vocoder based on the pitch-dependent directed convolution. We call it the QPNet. And this one can make the F0 control range wider. I mean, this network has a good ability for not only the interpolation, but also the extrapolation. Okay? And this one is very helpful for significantly reducing the network size as well. So if you are interested in these techniques, please register the tutorial. All right, so do you have any questions? Okay, if not,
okay.
So let's have a break.
Let's have a break. Okay, thank you very much, Tomoki.
Okay, so the next topic is the technique for making the training process more flexible. Okay. So the key ideas are how to generate the parallel data from non-parallel data. Here the parallel data means the utterance pairs of the source and target speakers. Non-parallel means we use the different utterances, different linguistic contents in the training. Okay? So the first idea is to generate pseudo-parallel data from the non-parallel data. The other idea is to factorize the speech to the speaker identity and the others. Okay? So as the parallel data generation approach, there are several conventional work. The first one would be the HMM state alignment to develop the parallel data from the non-parallel data. And some researchers have successfully applied the unit selection-based approach to generate the pseudo-parallel data. Actually, they use frame-based unit selection. And recently, the cycle GAN can be applied to the voice conversion, the non-parallel training case. This one could be regarded as one of the methods for the parallel data generation. By using the cycle GAN, we could generate the pseudo-training data, pseudo-parallel data from the non-parallel data. As a factorization approach, there are lots of the techniques based on the model adaptation. Okay? So the first one, some researchers have proposed a linear regression of the model parameters. And some researchers have successfully applied the maximum a posteriori estimation. And we propose the eigenvoice conversion. This is, I think, the one of the pioneer work based on the factorization of the speech signal into the speaker identity and the others. Okay. So in this framework, we have just started to use multiple speaker data sets. And then this one can be easily extended to the many-to-many EVC. So now we can handle the arbitrary speaker pairs, even if we don't have any parallel data. And recently, some researchers have proposed the method of using the speaker-independent features, such as a form posteriogram, the PPG for short. That is very helpful for handling the non-parallel data and the multiple speaker data. And the variational autoencoder is very effective for handling this kind of the problem. And by using this one, the non-parallel multiple speakers data can be well handled. And recently, this one can also be extended to the better approach using the GAN. Some researchers has applied the star GAN to the voice conversion approach, a voice conversion framework. And he has proposed another type of the VAE, the variational autoencoder. So the latent representation is given by the discrete variable, and they also use wavenet for the encoder and decoder. This is called the VQVAE. This is great. So now we can factorize the speech waveform directly to the several components. And we also developed some extensions of the VAE, but I will skip this one. So I will explain some of them one by one. Okay, so let me first briefly explain the two basic approaches to non-parallel data. The first one is a parallel data generation, and the other is a model adaptation. That is a factorization. Okay. So now we have the source data and the target data, but they have the different linguistic contents. Okay. And in this framework, we generate the pseudo-parallel data, for example, by using the frame alignment. We try to find the alignment between this frame and this frame, okay? And then finally, we generate this kind of the pseudo-parallel data, and by using this one, and we develop the conversion model. So this is a parallel data generation approach. The other approach is a factorization. Okay? So this is the very traditional, the original framework based on the factorization. In this framework, we use another parallel data. Okay. So by using the existing parallel data, we developed a kind of the canonical model. Okay. And then by using the non-parallel data from the source and target speakers, we adapt this canonical model into the desired speaker pairs. Okay. So let me explain the non-parallel training using the cycle GAN. But I have already explained the cycle GAN framework, so I will quickly look at this one. So again, this is the cycle GAN. So we have the two networks. The first one is a conversion network from the source to the target. The second one is a conversion network from the target to the source. We use these two types of the networks. And because of the cyclic GAN, so we use this cycle conversion. Okay. So this source data X is converted to Y by using this one. And this one is further converted to X by using this one. Okay. So this is a kind of the conversion from X to Y to X. Okay. And now that we can calculate the cyclic loss here. So we also do the same things from target to source to the target. Okay. And then we can calculate cyclic loss. And we also use this discriminator because of GAN, and we propagate this adversarial loss in order to optimize these two networks. And we also use the discriminator for the target space. This is a discriminator for the source space and discriminator for the target space. Okay? And we also propagate this adversarial loss from this one into these networks. Okay? And we also actually use the identity mapping loss. So we use this one as input of this one. Okay? We use this one as input of this one. Okay? So anyway, so by using these kind of the loss functions, we jointly optimize these two networks. So in this framework, we could say that by using this cyclic conversion procedures, we generate the pseudo-parallel data. Okay, so this one is a target, and this one is converted to here, and this one is this one is converted to here and converted to here. And now these two data has the same linguistic contents. So that's why we can calculate this cyclic loss. So in this framework, we generate this kind of the pseudo pyro data using the cyclic GAN. Okay. So next one is the factorization. So let me explain the old method first. That is the eigenvoice conversion. So in this framework, we use the multiple parallel data sets in advance to develop the canonical model. Okay? So the training data sets includes these parallel data sets. This is a reference speaker, and this is a pre-stored different speakers. So let's assume that we have this kind of existing parallel data. Okay? And by using this one, we can train this kind of the probabilistic model. So this is a traditional joint PDF. This is a reference voice, and this is a pre-stored target voice, for example. And we have the hidden variable here, like the GMM. Okay, and this one can capture the contextual information. So this one varies frame by frame. So this part that varies frame by frame. And here we have the multiple speakers, so that we use one more variable for representing the speaker ID, speaker identity, and that is given by WS. And this one affects the target speakers, the speech features. Okay, so this kind of the hierarchical variable dependencies that we can factorize the linguistic contents and the speaker-dependent contents. Okay? The point is the linguistic components varies frame by frame, and the speaker-dependent component varies, for example, the utterance by utterance. Okay? So such a hierarchical structure is very effective for modeling, for factorizing the linguistic contents and the speaker-dependent components. So in this framework, we use the existing parallel data so that we can use this reference speaker as an anchor point. Okay. So one of the popular approaches for such a factorization is the eigenvoice conversion, or EVC for short. So this one factorizes the GMM, the mean vectors, which is called the super vector, into the context-dependent and the speaker-dependent components. Okay? So this is a super vector developed by concatenating all mean vectors of the GMM. Of course, this one depends on not only context, but also the speakers. Okay? And this super vector is represented by this linear combination. So here we have the basis vectors. Okay? So this one handles the typical speaker variations. So this is the context-dependent part. And we have the bias vector. This is a kind of the average voice. Okay? And we have the factor here. So this one depends on the individual speakers. So we try to factorize this contextual component and the speaker-dependent component into the basis vectors and these factors. So we develop this super vector by the linear combinations of these basis vectors and the factors. And only this part that varies over the different speakers. Okay? The other parts are the fixed. Okay? The other parts are shared among the different speakers. Only this part that varies over the speakers, different speakers. So this is the eigenvoice conversion. And I will show you the very, very old demonstration. So I developed this one in 2006 probably. And in this framework, we use the EVC for performing the many-to-one conversion. So the arbitrary speaker's voice is converted into the specific target speaker's voice. So in this framework, first we perform the adaptation. Okay? So the probabilistic model was trained in advance using the multiple parallel data sets. And now we want to estimate, we want to infer the speaker, the dependent variable, given only the new speaker, okay? And here we don't need to use the parallel data between the X and Y. So we only have the only Y, okay? Then by using this one, we can infer the speaker, the dependent features. And then by using this one, we can develop the joint PDF so that we can perform the conversion from the X to Y or Y to X and so on. So here I will show you the conversion from the Y to X. I mean the conversion from the arbitrary speaker's voice into the specific target speaker's voice. So let's listen to the target speaker's voice. Again, the story in Japanese. Again. This is the target speaker's voice. And now I try to record my voice. So I will record only for 4 seconds. この声をさっきの声に変換してください。This is the vocoded voice. And now if I click this part, this system try to infer the speaker, the dependent feature for my voice, given my voice of the only 4 seconds. And then the system try to convert my voice into the specific target speaker. Okay, here we go. Okay, so let's listen to again the target speaker's voice. So this is a many-to-one conversion. So by using only my recorded voice of the only 4 seconds, we can convert, we can quickly develop the conversion model from my voice into the previously determined target voice. So this is the example of the factorization. And we can easily extend this framework into the many-to-many conversion. Okay? So the idea is very simple. Now we have the conversion from the arbitrary speaker's voice into the target. And we can also develop the conversion from the predefined source speaker into the arbitrary target speaker. Okay, so now we can combine these two conversion processes. So we have the conversion from the arbitrary speaker into the predetermined reference speaker, and we also easily develop the conversion from the predetermined speakers into the arbitrary speaker. So by combining these conversion models, we can easily develop the conversion from the arbitrary speaker into the arbitrary speaker. Okay, so this is a many-to-many conversion. So we can say that first we perform the speaker normalization here. So the arbitrary speaker's voice would be converted into the reference speaker's voice, and then this reference speaker's voice is further converted into the arbitrary speaker's voice. Okay. So again, this is the graphical model of the EVC, EVGMM, I mean the eigenvoice GMM. So we have this joint PDF, okay? So this is the latent vectors, capturing the contextual information, and this is the latent vector for capturing the speaker information. And because of this joint PDF, we can easily develop this conversion from the arbitrary speaker into the reference, and from the reference to the arbitrary speakers. Okay, so here this is the reference, the speaker's speech features, and this is the arbitrary speaker's speech features. As I shown in the demonstration, we can easily infer this one using only this data. Okay, so now we can combine these two conversion framework. Okay, we concatenate the one-to-many conversion model and many-to-one conversion model like this. Okay. So this part shows the many-to-one conversion as I shown in the demonstration, and this one shows the one-to-many conversion. Okay, from the reference to the arbitrary speakers. So now we can share these reference voices, and we can also perform the marginalization of this one. So we can marginalize out the reference speaker's voice. We can consider this one as a hidden variable. so that we can analytically derive the joint PDF between this one and this one. Okay, so this is the many-to-many the EBC. So the intuitively explained that we just do this one. Okay, so we perform the many-to-one conversion first, and then the one-to-many conversion. Okay. All right. So recently again we can implement the deep learning techniques. Okay. So now we can some researchers have successfully implemented for example the ASR, I mean the automatic speech recognizer in the voice conversion system, so that they use the phone recognizer for extracting the speaker independent contextual features. Okay. So now we have the source feature sequence, and by using the phone recognizers, this one is converted into the phone posterograms. Okay. So we can say that here we remove the speaker dependencies from the source feature sequence. We extract only the contextual features, I mean the linguistic features here. Okay. And then in this framework, they train the target-dependent conversion network from the PPG into the target acoustic feature sequence. Okay. So by using this one, they add the speaker dependencies here. So this is the overall structure using the speaker independent features. And the main advantage of this framework is we can no longer use the parallel data. So now we have only the target speech data. And by using the phone recognizer, I mean the pre-trained phone recognizer, this target speech data is converted into the PPG. Okay. We extract the speaker independent, the contextual features from this target speech data. And then we just train this generator. Okay. We just train the conversion network from the PPG to the target. Because of this one is a speaker, because this is a speaker independent feature, so we can just train the target dependent conversion network here, so that we don't need to use the parallel data. So this is the speaker independent feature extraction based on the PPG. Okay. And now recently lots of the researchers is interested in using the variational autoencoder in the voice conversion. So in this framework, we can use the multiple non-parallel data sets to develop the factorized conversion model, such as conditional variational autoencoder or adaptive restricted Boltzmann machines. Okay. So here I will show you the graphical representation of the conditional VAE, CVAE. Okay. This is the acoustic features, and this is the speaker dependent, the latent variable, and this is the context dependent latent variable. Okay, and by using the encoder decoder type network structure. First, the acoustic features of the speaker S is converted into this one. And this is the speaker independent, the contextual features. Okay? And then by using this decoder, this one is converted into this one. So this one will be reconstructed by using the cyclic procedure. Okay? And in this decoder network, we add the speaker representation. So by controlling this one, this network try to render the speaker representations into this generated acoustic features. So this is the conditional VAE. So in the training, we can use the multiple, non-parallel, data sets for optimizing these two networks. Okay. So that we don't need to use the parallel data. We just use the lots of the data from the multiple speakers. Okay? And we, for example, use the one hot representation here. So this is the deterministic variable. And then we just optimize these two networks using the prior distribution. Okay, that is the training step. And right, so consequently, we can train the speaker-independent encoder network. So this trained encoder network can convert the arbitrary speaker's acoustic features into the speaker-independent, the contextual latent vector. Okay? And this one becomes the speaker adaptive decoder. So by changing this speaker code, we can control the speaker representation of the output of this network. Okay. So this is the training. In the conversion, we can just use this encoder and decoder. Okay. So first we use the encoder to convert the source speaker's feature into the speaker independent, the context dependent feature. And then by giving the
We are encouraged by the news.
We are encouraged by the news.
Who was the mystery MP?
Who was the mystery MP?
Under Alex Ferguson, Aberdeen showed it could be done.
Under Alex Ferguson, Aberdeen showed it could be done.
And even beyond where the paddocks were, and the berry patches.
And even beyond where the paddocks were, and the berry patches.
And even beyond where the paddocks were, and the berry patches.
And even beyond where the paddocks were, and the berry patches.
And even beyond where the paddocks were, and the berry patches.
And even beyond where the paddocks were, and the berry patches.
And even beyond where the paddocks were, and the berry patches.
And even beyond where paddocks were, and the berry patches.
And even beyond where the paddocks were, and the berry patches.
And even beyond where the paddocks were, and the berry patches.
So can we just give me 1 minute?
Okay.
Change this.
Oh, much better.
Here probably, yeah. I think somewhere I was put in -10, so I put the 0 dip.
Okay.
I think it's, when you try, so
Okay, so in this, the first challenge, the system could achieve the 75% of the correct rate and the 3.5 of the most score, okay? So
Excuse me, sorry. Can I ask one thing?
Yes.
How was the naturalness? How was it evaluated?
Right.
By
so
human, machine?
Human.
Okay. Is it possible to do it? Like, are there any known good ideas to algorithmically test naturalness?
Well, we don't have any other good method for evaluating the synthetic voice. So that's why we just use human evaluation. Unfortunately, this is a very, very big problem should be addressed in this society, but we don't have we still don't have the good result. Anyway, so this is a result of the human evaluation. Though we present the audio sample to the listener, and the listener give the score of the naturalness. So this is a speaker's voice.
After such a fall as this, I shall think nothing of tumbling downstairs.
And this is the target.
After such a fall as this, I shall think nothing of tumbling downstairs.
And this is a top system.
After such a fall as this, I shall think nothing of tumbling downstairs.
Okay, so this was the result of the first voice conversion challenge. So we developed this top system successfully, and in this system, so that we use the direct waveform modification, as I explained in the previous slide. But unfortunately, we couldn't successfully implement the waveform modification for converting F0. So in this system, we used vocoder. So this is a very pity. Anyway, so first the input speech is converted using the vocoder. So that we convert the F0, the excitation parameters first. And then we perform the direct waveform modification based conversion. So by using this, the F0 converted voice, the excitation parameter converted voice as an input, we estimate the time variant filter. And then this time variant filter is applied to the excitation converted features, excitation converted waveform. Okay, so this is the system developed in the first challenge. So unfortunately, in our internal listening test, the performance of this system is comparable to our previously developed system more than 10 years ago. So it was very disappointing. So anyway, so we had the second challenge in 2018. So we set the two tasks. The one is a hub task for the parallel training. The other is a spoke task for the non-parallel training. So again, we evaluated the naturalness and the similarity by listening test. This is a human listening test. And we also calculated the word error rate and the spoofing results. And this is the evaluations using the countermeasure to detect the synthetic voice. I mean the distinguished synthetic voice from the natural voice. Okay. And we designed the VCC, the 2018 dataset. And here in the second challenge, we use the 22.05 kilohertz sampling rate. And we prepare the parallel dataset and the non-parallel dataset. Okay. So this is a result of the second challenge. The 23 systems were submitted, okay? And this is a result of the parallel data, and this is a result of the non-parallel data. The horizontal axis and the vertical axis are the same as the previous challenge. So here we have the very strong team here, a strong system. And this is a natural source, and this is a natural target. Previously, the base system is around here, but now we have this one, okay? Unfortunately, this was developed by, not my group, but the different group. But this is great. And interestingly, this one has almost the same result in the non-parallel data. So this is very strong. And this is a baseline system. So in the hands-on session this afternoon, we will learn how to develop this one. Okay. So by using the freely available software, we can develop this one. And in this challenge, we developed this system. Okay. So this is ours. So let's listen to the audio samples. And this is a source.
This even tint was indeed broken up by streaks of yellow sandbrake in the lower land.
And this is a target.
This even tint was indeed broken up by streaks of yellow sandbrake in the lower lands.
And this is a baseline.
This even tint was indeed broken up by streaks of yellow sandbrake in the lower land.
This is ours. Oops.
This even tint was indeed broken up by streaks of yellow sandbrake in the lower land.
This is an excellent system.
This even tint was indeed broken up by streaks of yellow sandbrake in the lower land.
Again, this is a target.
This even tint was indeed broken up by streaks of yellow sandbrake in the lower land.
So I will briefly explain the contents of individual systems. So this is a top system, okay? So this one uses lots of the external data. So they use the ASR for extracting the speaker-independent features. And this ASR system trained using the hundreds of the hours of the external data. So anyway, by using ASR, they first extract the speaker-independent, the bottleneck features. And then this one is converted into the target speech parameters using the target-dependent, the network generator, okay? So to train this one, they use the VCC 2018 dataset consisting of around 80 utterances. And then they use the WaveNet for converting the speech parameters into the speech waveform, okay? To train this WaveNet, they also use the external data, okay? 80 hours of the external voices, and they perform the fine-tuning using this target speakers data, okay? So this is the structure of the top system. And by using this speaker-independent features, this system doesn't need to use a parallel data, okay? First, all data can be converted into this speaker-independent features. And then this one is converted into the target-dependent speech parameters. So that we no longer need to use the parallel data. So that's why this system has the same performance between the parallel VC and the non-parallel VC. So this is the second system, actually developed by our team. And we use the traditional VC framework. we just perform the vocoder for extracting the speech parameters, and then we perform the speech parameter conversion using the deep network, okay? And then we use the WebNet vocoder, okay, to convert the speech parameters into the converted speech waveform, okay? But actually, we don't use a huge amount of the external data. We just use 2 hours of the external data, and we perform the fine-tuning using this BCC 2018 dataset. So this is the second system. So we have the common factor here. So both system uses the WebNet vocoder, okay? So the neural vocoder is very effective for improving the converted speech quality and conversion accuracy, actually. And the last one is the baseline system. So this was developed by using the Sprocket. That is a freely available software. So the Sprocket implemented the 2 types of the conversion. The first one is a direct waveform modification. The other is a vocoder-based generation. So we use the waveform modification for the same gender conversion because we can avoid performing the F0 conversion. But on the other hand, for the cross-gender conversion, we should perform the F0 conversion as well, so that we use a vocoder, okay? So for the same gender conversion, we perform the direct waveform modification to generate converted voices. And for generating the converted voices for the cross-gender VC, we use the word vocoder. Okay. So this is the system structure of the baseline system. And this afternoon, we will use this one. We will develop these baseline systems. So now 2020 is approaching. So we hope that we will hold the BCC 2020, but the time is limited. So and now that we have the very good conversion system, lots of the research group have successfully applied end-to-end, the encoder-decoder network to the voice conversion. So now I think the speaker conversion can be solved. So the tasks that should be more challenging, okay? But anyway, so any comments and requests are very welcome. And if you are interested in helping us, please contact me, okay? All right, so the last topic is the development of the various applications. So the voice conversion is a very generic technique, so that we can apply these VC techniques to various mapping tasks. And actually, there are lots of the big possibilities to develop the various applications using the real-time voice conversion. Okay. So so far there are lots of the research for the applications, but here I will briefly explain the applications based on the real-time voice conversion. We call this framework the augmented speech production. As I explained in the beginning, the voice conversion can be used for augmented our speech production. So the first application would be the speech enhancement for the handicapped people. And the second one is telecommunication. The third one is kind of the entertainment, as I showed in the demonstration. So that now we can sing or speak using the specific target, the speaker's voice. Okay, so in these applications, we need to develop the real-time, the statistical VC. So as I explained, we basically use a sequence-based conversion. Okay, but in order to do the real-time processing, we need to achieve the short latency, so that we approximate this batch-type conversion with the low delay frame-wise conversion. Okay, so we use some delay, and we propagate the old past information into the next. Okay, and by using the future frames, we determine the current result, the frame by frame. Okay, So this is the real-time conversion. So the first application is a speaking aid. So here our target is the laryngectomy, who lost their own vocal folds due to for example, the laryngeal cancer. Okay. So they cannot produce speech sounds in a usual manner, so they need to use some devices or the special speaking method. For example, in the esophageal speech, they try to push air from the mouth to the stomach, and then this air is back to this vocal tract to vibrate these soft tissues. And this is a esophageal speaking style. And by using this one, they can produce this kind of voice sounds. So that we can still listen to the linguistic contents. So we can use this spectral envelope information. But for the F0 and the periodicity, I mean the excitation parts, we cannot extract the useful information. So we develop the conversion from the spectral envelope into the normal speech parameters, including not only spectrum, but also the excitation parameters. So the F0 patterns are also estimated from this spectral information. Okay. So this is the result. This is the input. So this is an example of the augmented speech production beyond the physical constraints. The second application would be the silent speech communication. And here we use the very special microphone attached to body. Okay, so this is called non-audible murmur microphone, and this is very similar to the stethoscope used by the medical doctor to hear the heartbeat. Okay, so we put this special microphone to this place and to detect the air vibration in the vocal tract through our soft tissue. Okay, so like the stethoscope, this one can detect very, very soft sound in the vocal tract. So even if the speaker is surrounded by the other people, she can speak very softly. Okay, so these people could not listen to her voice, could not hear what she said. But by using this special microphone, we can detect this kind of sounds. Sorry, in Japanese example, but we can detect this kind of murmur. Okay, now this is a body-conducted voice, and intelligibility is very poor because of the body conduction. So that we use a real-time VC. So we convert this less intelligible voice into the intelligible voice. So if we convert this one into the normal voice, this one becomes this one. So this converted voice can be conveyed to only the listener. So in other words, we can develop the kind of telepathy like communication. She can convey what she says to only this person, okay, while keeping the others secret. Okay. So this is an augmented speech production to develop the telepathy like communication. The last one is entertainment purpose, the vocal effector. So here I will show you one example of the vocal effector to control the perceived age of the singing voice. So by using the eigenvoice conversion framework, we can develop the singing voice conversion capable of controlling the perceived age. So first, we manually assign the perceived age to the individual singing voices, and then we train the eigenvoice conversion for controlling the converted voices given the perceived age. Okay, and then by using the developed conversion model, we can control the perceived age of this singer's voice. Okay, so that this is the original singing voice. So let's make this singing voice younger. Or elder. So I will play these samples from the younger to elder. Okay. So actually we cannot have these voices. Okay, these voices don't exist. Okay, but we try to guess the voice quality if she becomes elder. Okay, so the idea is we developed the speaker independent subspace spanned by the perceived age using these multiple singing voices. Okay. So that we can do it by using the machine learning. Okay, so I will explain these techniques. Let me summarize this class. So I will focus on the advantage of the voice conversion techniques, but we should also focus on the risk of the voice conversion. Okay, so that we need to look at the possibility that the voice conversion is misused for spoofing. Okay, especially by using the real-time voice conversion, we could speak using someone's voice. So this is dangerous actually. But in my opinion, we should not stop the VC research. Okay, there are lots of useful applications for helping the people. Okay, so recently we have just started to collaborate with the speaker recognition, speaker recognition society, and they has just started the anti-spoofing challenge SB Spoof since 2015. So that we have the collaboration. So we prepared the spoofed voices using our voice conversion technologies. And then they try to develop the better countermeasure to detect their synthetic voice generated by our technologies. Okay, so we have the collaboration between this ASB spoof and the voice conversion challenge (BCC). But this is a kind of how can I say, the no goal of the activity. So if they find the better countermeasure, probably we can implement the countermeasure as objective function for training the network. So the more essential solution would be to widely tell people how to use a statistical VC. I mean, beyond the researcher, we need to tell the general people about how to use the statistical VC. Okay, this is more important. So it is important the general people understand the VC needs to be socially recognized as a kitchen knife. Okay, so we need to correctly use the VC, so that we can know how to use a kitchen knife. So we need to tell the general people how to use the voice conversion technique. Okay, so that is a more essential solution, I think. All right, so let me summarize this talk. So I will briefly explain the basics of the voice conversion. So there are many useful VC applications. And statistical VC can be achieved by using the signal processing and machine learning. And we looked the VC research history and recent progress. For the conversion model, now we have the very good nonlinear sequence mapping, especially using the encoder-decoder with attention. So for the objective function, now we can use a GAN, okay? So we can use a data-driven optimization function. So for the waveform generation, now we can use a neural vocoder. So we can generate the very natural speech waveform from the given speech features. For the flexible training, now we have the good data-driven factorization, such as the VAE. And for the technique comparison, now we have just started the BCC, so I hope that someone help us. And for the application development, so now we can develop the real-time BC, so we may develop the new service for helping the people. So the more important point is the risk of the BC. So let's tell the general people the BC is something like a kitchen knife. Okay, that's all my talk. Thank you.
So for speech impaired people, obviously you don't get pitch information. So my first question will be, how do you deal with this in real time? And the second question will be, what about tonal languages?
Right. Actually, the Japanese is a tonal language. Okay. We have the special F0 patterns in each word. But even in such a language, we may predict the F0 patterns from the spectral components. So this one includes the linguistic contents, so that we may predict the F0 patterns. Actually, but the accuracy is not so good. The correlation coefficient between the predicted F0 patterns and the natural one is around 0.5 or 0.6.
And so this is possible to do it in real time?
Yes.
Okay.
Did you also use the text information for all this training?
And we can use it, but here, in this case, we don't use it. But as I explained, recently the PPG can be used for the conversion, so that we could implement such a text information. And some researchers have successfully implemented the adversarial loss of the phone recognizer for improving the network. I mean, in order to generate more intelligible voice, the adversarial loss from the phone recognizer is very helpful. So that, we can use such a text information.
Thank you.
Recently I learned that some scientists have been able to map from brain signals to speech. So do you think the voice conversion community should jump into that area?
Well, I know some colleagues of the AMLAC, has joined such a research project, but it is still very big hurdle. That we need to detect the clean brain signal, but it is very difficult, especially. So this is my opinion. So now we focus on the use of the different modality signal. So actually we don't have to use a brain signal. I mean, even if some handicapped people, they can still move the other parts. So this remaining function could be used for controlling the voices. So that we can use additional signals, except for not only brain, but also the others. Not only brain signal, but also the other signals can be used for controlling the voices, I think.
One comment on that. That is a very good point, Tomoki. This also was an effort many years ago to control through the HMM synthesizer playing music or singing. And Christophe D'Alessandro and Thierry Dutoit, they've done a lot of work on that. So it's exactly a lot of modalities that we can explore for such a purpose.
Right. So I believe the ability of the human adaptation is very good. So if we can develop such a real-time system, probably the people can learn how to use or how to move for example, body to well control the voices through the interaction between the system and users. Yeah. So I hope. Yeah.
One more question. Also, the mood. Can you infer the mood on the generated sound, or it is transferred also from the source to the target? I mean, the end result would have the same mood as my recorded voice? Sorry, or it will have the same mood from the voice used on training?
I see. So the mode means the kind of the speaking style, for example, right?
Yeah.
So the key idea would be the factorization. So if we develop the good network to factorize the speech signal into the individual components, so that we could control our desired mode while keeping the other factors. For example, keeping my speaker identity, that we could control the speaking style only, and so on. So any other questions?
Probably not. It's time to go for lunch. Okay, thank you very much again.